Hello! Today we are going to start talking about optoelectronics. That's the electronics related to light. But before we do that, we need to talk about some other subjects such as the nature of light, a little bit about optics, and of course how laser works. So let's get started by talking about the nature of light. So let's go over a couple of things that maybe we already know and then go on beyond that. So we know that light is an electromagnetic wave. So it's a wave in the space-time continuum that has magnetic fields and electric fields. And we also know that light has a wave-particle duality. In other words, if you look at it as a particle, it acts like a particle. But if you look at it as a wave, it acts like a wave. So it seems to act like both at the same time until you decide which way you're going to look at it. So let's see if we can demystify this a little bit and see how light works and what it is. Keep in mind that I am not a physicist and my knowledge about this has a few gaps, but I've looked into some of the leading edge theories about how light works, and I'm going to give my best rendition of that. So again, keep in mind that this is quantum physics according to Bob and is subject to change. So let's look at the birth, life, and death of a photon, which is what we call a particle of light. So I'm going to go out 2.5 million light years to a galaxy way out there. This is the Andromeda Galaxy. Why do I pick it? Because we all know about the Andromeda Galaxy, and I'm representing it as a dot with these spiral arms. And so somewhere in one of these spiral arms is an electron. And this electron has a certain amount of energy, but like electrons often do, they will randomly lose this energy and go from one state of energy down to another. And when they do, they cause a disturbance in the space-time continuum. In fact, it seems from what I've been able to read is that the current theory about the nature of the space-time continuum is that it is some kind of a uniform electric field. So when an electron drops from one energy level to another, it creates a disturbance in this electric field. It's a lot like the disturbance in a pond when you throw a rock into a pond. We talked about that in the nature of sound. So you drop a rock into a pond, it causes a disturbance, and that goes out as an energy wave where we trade potential energy for kinetic energy back and forth as the wave goes through that medium. Well, the medium here is this electric field that space-time consists of, and what we're going to get is a wave of electric polarity. So this wave goes out. I'll look at the nature of its polarity in a moment, but this wave starts to go out. Now, if we take a look at the light as a particle for a moment, one thing we know about light is that it has no mass. So according to Newton's second law, which is your force equals your mass times acceleration, what that means is that our acceleration is going to equal our force divided by our mass. And since this mass is 0, that means we're dividing by 0, which doesn't work. But we know that if we approach 0 and divide by numbers approaching 0, we start approaching infinity. So that means our acceleration should be infinite, or close to infinity at very least. So what does that mean? That means that that light wave that we develop in the space-time continuum is going to go at an infinite speed and in all directions at once and fill the universe instantly. Well, we know that doesn't happen. Why? Well, because quantum physics and because of special relativity also, the speed of this light wave is limited by special relativity. I'm not going to go into that now. I'm going to go into that in a completely different, unrelated video in my relativity class. But we do know that the speed of light is limited to very close to 300 million meters per second. It's 299 million something meters per second. Exactly, no decimal point, because by definition that's the speed of light. But we'll just round it up a tiny bit to 300 million meters per second for this discussion. So there we have this light expanding at 300 million meters per second. So what does it look like? Well, it's expanding in all directions, so it's like a bubble. And I'll just draw that as some circles as it expands, because I can't draw three-dimensional objects on a two-dimensional whiteboard. So that's expanding, and the radius of that expansion is going to be the speed of light, or 300 million meters per second. Now as that expands, it expands through gases and dust and other stuff inside the Andromeda galaxy. And every time it encounters an electron, there is a chance that it will interact with that electron. That chance is incredibly small, but the chance does exist. And because there's so many electrons that it might interact with, the chances of it interacting with one of them is actually non-zero. But the chances of interacting with any particular one is almost zero. But nevertheless, there are so many electrons it might interact with, it could interact with one. But let's not talk about that yet. Let's say this one doesn't interact with anything, and 2.5 million years later, it reaches, well, I'm going to, instead of saying my eye, I'm going to use a photodiode because I can say something particular about that. So here's a photodiode that is trained in that direction. And finally, this photon reaches that photodiode. And there's a number of electrons in that photodiode. And particularly, if we look at the crystal structure, we have some silicon atoms. Each one of those has 4 electrons around it. Actually, it has 8. I'm going to go ahead and draw 8 because there are going to be 4 more that belong to other atoms around it, creating the covalent bond that is the structure of the silicon crystal. And let's say that one of those adjacent atoms is an arsenic atom, which also has 8 electrons around it. I'm not going to draw those because, well, I guess I could. Because it fits into the covalent bond structure the same way, but this arsenic atom has an extra electron in its valence shell of electrons that doesn't fit into this lattice work. So it's going to kind of hang around this atom. I'll just draw it. I'll make it a dot. So it's going to hang around this atom, but it can't fit into the crystal structure, and it's not bound very tightly in there. And so let's say this particular electron just happens to interact with this photon, which is a big bubble of photon energy, and it kicks it into a higher energy state. And that's a high enough energy state that it can disassociate from this atom and move freely. And let's say that there's a positive charge here and a negative charge here, and that's going to cause that electron to want to move in that direction. And because of the energy that it absorbed from this photon, it's able to move and flow as part of an electrical current. Ta-dam! We have just detected that photon. What happened to the energy in the photon? Well, that photon contains a certain amount of energy, and it contains no more, no less. It cannot contain anything between certain levels of energy. We're starting to talk about quantum physics here. So that photon is going to either interact with an electron and lose its energy or not, one or the other. So it interacted with this particular electron, kicked it into a higher energy state, and that energy was absorbed by this electron. So what happened to the energy in this photon that now is 5 million light years across? It's gone. Completely disappears. Now, it could have interacted with electrons almost anywhere. It may have interacted with an electron over there, in which case it couldn't have interacted over here. But it's gone. As strange as that might seem, the best I can see, that is the current theory on the nature of a photon, is that it does this thing. But you say, but nothing can happen faster than the speed of light. The current theories are that information cannot be transmitted faster than the speed of light, but quantum things can happen instantly across vast distances in space. You may have heard of quantum entanglement, and that's one of these things. I don't know if there's a direct relationship between this and quantum entanglement, but quantum entanglement is another thing where stuff can happen over vast distances instantly, but of course we cannot send information faster than the speed of light. Weird things are happening here. I don't fully understand it, and I'm in good company because Richard Feynman said, if you think you understand quantum physics, you don't. So that leaves us at that point. So just to reiterate this quickly, because this is probably something really new to you, this photon started out as a disturbance in the space-time continuum 2.5 million light years away, and this spread as a sphere of energy at the speed of light, 300 million meters per second. So the diameter of the sphere is spreading at twice that speed. So it's The radius is spreading at 300 million meters per second, so the diameter is spreading at 600 million meters per second. It's getting bigger and bigger. It may or may not interact with electrons anywhere along the way. Very small chance of it interacting with any particular electron, but because there's many, many, many electrons, it has a high chance of interacting with one of them. But somehow this one makes it all the way down to my little diode here, interacts with an electron there. That energy is completely absorbed by the electron. The photon is now gone, it has died, and it becomes the energy in this electron that allows it to come out of its crystal lattice and now move as an electric current. What does it tell us? So let's take a look at what we think we just saw here. We know something happened way over here, and then in a straight line between it, nothing else happened, and then finally an event happened over here. And we see that that event contained a certain amount of energy, and that energy was completely absorbed and taken away. And therefore, that entire photon collapsed. So we saw something happen here, nothing happened in between, almost straight line there, and then it caused something to happen there, and then disappeared. Looks like a particle, doesn't it? So it acted like a particle in that case. But we know that it was actually the sphere of energy, and that energy was completely absorbed, but it could have happened almost anywhere. So what's the actual nature of this? Well, let's take another step and take a look at that. Let's get rid of this clutter here. In fact, let's just start over. We have our galaxy out here. The photon is created by an electron dropping to a lower energy state, and that bubble spreads out. Let's take a look at part of that bubble. We're going to just cut a square out of it. In fact, we're going to be so far away that these lines are basically parallel. So this bubble has come all the way to the Earth. It is so big now that from our perspective of looking at what part we can see, near as makes no difference. It's just a flat plane. So here's this flat plane coming at us. I want to get rid of these lines for a second, and I'm going to just cut part of it out. So here we go. I'm cutting at an angle because it's coming from there. And so we're going to cut a square out of that plane, and we're going to examine it. We're going to find that it's positive in this direction and negative in that direction. So we've got an electric field disturbance in that direction. If we look at it when it was smaller, when it was still the sphere, we would find that it was positive here and negative there. And we find that if we follow the lines of the curvature around this bubble, we can see that this is most negative, less negative, less negative, less negative, more positive, more positive, more positive as we go around these lines that look a lot like the longitude lines on a globe like the Earth. And so there's the distribution of our electric field. But we also find that there is a magnetic field around the equator of this bubble, in which we have, it's a little hard to draw here, but we can analyze this as little tiny magnets that are going north, south, north, south, north, south, north, south. So we have a magnetic field where north is kind of one way and south is kind of the other way. It's a little different because if you chop it into smaller pieces, you get smaller and smaller magnets, but the north is always on one side and the south is always on the other. So we get south, north, south, north, south, north, all the way around that. And we have rings of that like rings of latitude in that direction. So we have this electric field and that magnetic field that are oriented 90 degrees to each other. Now, one thing to remember here is that a magnetic field is actually an electric field observed from a different frame of reference. So when we have a magnetic field around a wire, that's actually an electric field. If we have a moving frame of reference where we're moving with those electrons in the wire, we find that's actually an electric field. But I have a whole different video about that. So we'll just look at it as a magnetic and electric field at this point. So by the time this gets to us, we're looking at just part of it, and we see that we have positive one way, negative the other way, and we have north on one side and south on the other side. So we have this electric field oriented this way and a magnetic field oriented that way, and this just extends all the way around the bubble. Like I said, the positive goes all the way to there, the negative goes all the way to there, and that extends around that way, and the little north and souths extend around. But from our place, we just see a field that's, I'll kind of come your direction here, positive here, negative there, north there, south there, when we see this field coming at us. So now we're going to get into something I'm a little bit fuzzy about because I'm not quite sure of the exact nature, if we can do this with one photon or multiple photons, but I'm just going to assume that one photon can have multiple fields in it. Let's say this photon is coming along and we actually have, well, let's bring this origin down to here. So the photon started there, and now we have this bubble. And if we look at maybe just this part of the bubble, we would see that there's multiple fields, as I described. And I'll say one is positive to negative, negative to positive, positive to negative, negative to positive, positive to negative. And so it's not just one, but it actually has some depth to it. And this is the strongest one. This is a little bit weaker. And this is, I'll just make that a dotted line here showing that's weaker. And it kind of fades away. If we draw a graph of this, I kind of don't like doing this because it gives people the impression that this is what light looks like, but we're going to draw a graph of the power. So we have steady state in the medium, and then we get something that looks like this. So there's the main pulse of the photon with our positive at top and negative at the bottom. And the other pulses, there's the negative to positive, positive to negative, negative to positive, etc. And they get weaker as they go along. It may have that kind of structure, and it may take multiple photons to create this structure. I'm not 100% sure, but I'm kind of leaning toward this kind of structure. So it looks like, well, that looks like a wave. It's really changing fields, and of course in between here we have different amounts of magnetism and electricity. Keeps reversing polarity, so we get this wave shape. So we saw the photon looked like a particle. Now we can see that it sort of looks like a wave. So it seems to be both things at one time. But I think you may have seen that the particle phase is really more of an illusion. It's the way we measured it, and we saw how it had a certain amount of energy and released that energy in a certain point. And it looks like, well, that must have been a particle, where it actually was a wave. But still, nevertheless, when this wave interacts with an electron, the entire thing over that whole area disappeared. So remember that this is a graph of these electric and magnetic fields. These are part of this bubble, which has now become absolutely huge. But once we interact, it's gone, because that's the nature of quantum physics. It probably sounds very weird to you, and I don't know if you're following it that well, but that is the nature of light, as I understand it, why it can act as both a wave and a particle at the same time. So now that we've established that light is a wave, let's see what things we know about it as a wave. When that photon was created, it had a certain amount of energy, and that energy is going to be directly related to, remember that little drawing I made? What we're going to have here, well, there's going to be a distance between these peaks here. And that's called the wavelength. So if you look at waves in an ocean, you see a wave here and then another wave there. The distance between those waves is the wavelength. So how far apart are these when it comes to light? The closest they can be is about 400 nanometers. And because that is the technical end of our visibility for short wavelengths. Anything shorter is ultraviolet light. Now, in reality, we can see some wavelengths of ultraviolet light because this number is actually where our eyes are half as sensitive as they are to the peak wavelength, which is somewhere in the green light area. But 400 nanometers is technically the start of ultraviolet light. And longer wavelengths, the longest one we can technically see is 700 nanometers. Which is the beginning of infrared light. So wavelengths longer than 700 nanometers are considered infrared. We can actually see some of those wavelengths. For example, in my fiber optics class, we used testers that used LEDs that emitted light at 850 nanometers, definitely in the infrared range. But you could look at those LEDs and you could see them. They were a very deep rust red color, but you could see the light from them because This is where our eyes are half as sensitive, but as we go deeper into the infrared, our eyes become less and less sensitive. And at 850 nanometers, which was the wavelength of those LEDs on the tester, you could still actually see it. I don't know of a number in here. I've never looked at an ultraviolet light knowing exactly what the wavelength was and seeing, oh, I can see that particular wavelength. And I don't know how sensitive my eyes are to this wavelength, so I can't give you any numbers, but we're going to be able to see somewhere into this region, and we can definitely see into that region. So the visible light is going to be light where the strong parts of the magnetic fields are 400 nanometers apart or as long as 700 nanometers apart. This is the start of ultraviolet. That's the start of infrared. So I have these very, very short wavelengths. Now this wavelength is also related to something else, and that is if you're standing still and this photon comes by you, you're going to see these waves come by at different times. So let's say just for whatever purpose, let's say these were 600 nanometers apart. I think that's green light, somewhere in the green area. Now don't quote me on that without checking up on me, but that's somewhere near green, yellow or green or something. And so 600 nanometers apart, and they're coming at me, so they pass me by. So how fast are these going to come by? I'm going to see this one, that one, that one, that one, that one, in quick succession. How fast? Well, to figure that out, let's go to a much, much lower frequency. So let's say we have an AM radio station transmitting at exactly 1 megahertz. So what we have is a electric energy going up and down this antenna 1 million times every second, and that's doing the same exact thing as we had that little thing happen up in Andromeda, except it's happening on a much bigger scale. And so this is creating a disturbance in space-time, and that's going out as a continuous wave because we're forcing this to be continuous. We're keep that electricity going up and down that tower, and so we have these waves going out from there. So it's going to be, here we go, positive to negative, negative to positive, positive to negative, negative to positive, etc. And our wavelength will be that distance there. Okay, so these are happening 1 million times per second, so 1 megahertz. So if I'm standing watching those come by, I will see this one come by, then that one come by, and then this one come by, and the time between this one and this one is going to be 1 millionth of a second because that's happening 1 million times per second. So how far apart are these? Well, they're traveling at what speed? The speed of light. At 300 million meters per second. So I find that the distance between here and here is going to be 300 meters. So I find that at a wavelength of 300 meters, I have these coming by me 1 million times per second, and they're being produced by the electricity going up and down this antenna 1 million times per second. So that's a pretty big wavelength, but now we're going to squeeze those together, and let's get in the infrared light because it's a nice easy number. So now I'm going to draw them bigger because I can't draw this small. Now let's go positive to negative, negative to positive, positive to negative, etc. And now these two are 1,000 nanometers apart. So it's in the infrared range, and you cannot see this. You can see 850 nanometers, but not 1,000 nanometers. But I picked that because if we do the math, these are coming at us at 300 million meters per second. They're 1,000 nanometers apart. So how often are they coming? They're coming start drawing some zeros. Did I get this right? Million, billion, there we go. 1 trillion times per second, or 1 terahertz. So if these waves of electromagnetic energy are coming at me and they're hitting me once every 1 trillionth of a second, that means that they're 1,000 nanometers across, and that is infrared light. So I'll put a little IR there. And of course, as these get shorter, they get closer and closer to the visible light. When they get down to where they're only 700 nanometers apart, I can start seeing them. And I'm not going to do the calculation for the frequency, but the frequency is simply the speed of light divided by the wavelength. So c represents the speed of light, lambda represents the wavelength, and so you can go ahead and calculate that out for whatever frequency you want. I use these because I didn't have to calculate it. So that is our relationship between our frequency and our wavelength. It's because the wave is traveling at a certain speed. There's a certain distance between the polarizations of that light, or if we're looking at this as a graph of a wave. Let's see if I can draw this correctly. There we go. So there's our negative peak, a positive peak, negative peak. The distance between those is the wavelength. So there's a certain distance, they're coming at a certain speed, so how fast they pass by us is going to be related to that. So we have our frequency and our wavelength, which are closely related. So if I relate that back to our radio wave, because I think that might be a little easier for us to wrap our minds around, there's our tower at 1 megahertz. So we have a radio wave coming out. And our positive peaks are 300 meters apart. That frequency is equal to, once again, 1 megahertz. And the wavelength is equal to 300 meters. And so there's the relationship. And once again, the formula is our frequency is equal to our speed of light divided by our wavelength, or our wavelength is equal to the speed of light divided by the frequency. So there's the formulas to figure that out. So the nature of our light wave is that it has the same relationship of any other kind of wave. Here's an electromagnetic wave of a much lower frequency, and we can see that there's a direct inverse relationship between the wavelength and the frequency. So we'll take a look at that at another time when we need to. So that's a couple of the aspects of light, is it has a wavelength and a frequency. Another thing to think about between our wavelength and our frequency, if I draw a wave such as this, let's say I have another wave that's the same exact frequency and even the same exact amplitude. The amplitude is going to be the size. So that's another aspect, is the amplitude, how big it is. And we notice that the amplitude can be different for different parts of a photon, for example. But let's say we have another wave that's the same frequency and the same amplitude, but it's happening a little later. I'll just draw it right here. Trying to draw it the same frequency and same amplitude. Did a terrible job there. But it's happening later. So what we have here is what's called a phase difference. It's basically a timing deal, and the peak of one wave is happening at a different time than the peak of another wave. And how we measure that is in degrees, because a wave can be broken down into cycles. So we have a complete cycle there and a complete cycle there. And there's a direct relationship between that and a circle. So I have a CD here, and oh look, there's a black mark on it. And if that CD goes around in a circle, that black mark goes around how many degrees? 360 degrees. So if I turn that sideways, and now I turn it, you can't see it, but it's going to be going up and down from your point of view. Now, if I have it go across your line of sight as it's going around and down, it's going to make this particular shape. So I can say that one cycle is 360 degrees. We talked about this in alternating current, so I don't need to go too much deeper into it. We already talked about phase and such. I'm just reiterating. And so how far apart are these? It's a certain number of degrees, and this is looks like maybe about 70 degrees out of phase there. So that's another aspect of the wave. We have the frequency, we have the amplitude we just talked about, that's how big it is. We have the wavelength, and we have, when we compare one wave to another, we have a phase. So let's start taking a look at some of the nature of light. And what's another thing we can look at? We can look at polarity. The polarity would be the orientation of this electric field. So right now our polarity is vertical because our electric field is oriented plus to minus or minus to plus, and our magnetic field is horizontal. So the polarity is the orientation of your electric field. So what if this was turned 90 degrees. Well, then our polarity is turned 90 degrees. So we have the polarity of that field. And people will say, well, it's vibrating this way or vibrating that way. Don't get into that, because that's that model that they show where the energy is. This is not really vibrating. It's really just pulses of energy going by. And so it's positive to negative, negative to positive, positive to negative. So our electric field is oriented this way. It's vertically polarized. If we turn it sideways, it's horizontally polarized. And if we turn it all the way upside down, it's still vertically polarized, because now it's just flipped. Now it's going to be negative to positive, positive to negative, negative to positive. Nothing's really changed. That is important in radio waves. We'll talk about that down the road, about orienting your antenna. But when it comes to light, that's important to some other properties that we will see down the road. One thing is that you can filter out different polarities and see different things because of that. Because sometimes light coming from an object is polarized. Most of our light is not. It's just different polarities just coming one after the other. Some light is this way, some light's that way, some light's that way. Most of our light is unpolarized, meaning it's just different photons oriented different ways. But if we have all of our photons oriented one way, we now have polarized light. And some things that emit polarized light, we can look at it through a filter that eliminates unpolarized light, and we can see different things. Look at that down the road.